Okay, hi guys, and welcome back to the channel. Now, recently a viewer shared something rather intriguing with me. A video that left me scratching my head. In it, we see someone using a test pen on what seems to be a set of ordinary rocks. But there's a twist. These rocks have ferromagnetic properties, meaning they are attracted to a magnet. Now, from what I can gather, the purpose of this video was to show off some kind of conductive property in the material. But there's just one problem. It's missing context, and without that, the demonstration falls flat, leaving viewers with more questions than answers. So today, I'm diving right into it, and now I'm going to break down the mechanics of this curious result, unpack the science behind it, and yes, reveal the fallacies lurking in that demonstration. But before we get started, there's one thing I need, that exact same test pen from that video. Hang on tight, I'll be right back. Okay, and here we have it, the exact same test pen as seen in the video. After zooming up close, it is beyond a reasonable doubt that this is the same test pen used. A typical test pen designed with an updated innovation. Now, unlike its previous generations of test pens, which consists of just a resistor to detect live voltage like this one here, this modern variant features an additional unique feature. There is a circuit board that detects ambient resistance, which is the neutral inductor. And then also it can detect the live. If there is a live voltage, the LED within this will glow red. If it's a neutral inductor, it will glow green. To power up the board, it requires some microcell batteries. Now, when properly powered with the batteries, by simply touching both ends of this test pen will offer an indication if the subject possesses some form of induction current and voltage. Likelihood, a neutral induction current is depicted by the green LED indicator. Now that we have our test pen tested operational, let's go about proving the fallacious nature of the video we are referencing. According to this video, a sample of rocks believed to contain iron or some other metals with ferromagnetic properties is further believed to contain conductive properties from the demonstration that the test pen lights up. It is claimed in the video that there is a current since the test pen lights up, and it can be concluded that the material is conductive. Now, I would like to highlight some flaws to this observation statement. First, just because the test pen lights up is not conclusive that the material is a conductor. There are several factors that needs to be isolated first. The surrounding environment too can result in a false reading that may sway conclusions. Now, allow me to demonstrate this. But before that, allow me to highlight the following precautions. With regards to the test pen, not all test pens are made equal. The more traditional test pen like this one here measures the presence of voltage between 100 to 150 volts. Whereas this one detects from as low as 12 volts to 120 volts, and this one is able to detect induction resistance as well. What this means is that it can detect electromagnetic fields that is present within a material, even if it is insulated by way of induction. For example, an electrical wiring, a copper core, is insulated by its PVC material casing. However, its internal copper wire has its own ambient EMF signature, which this test pen can pick up, which allows faster identification of where a break might have occurred internally in the wiring. When the two contact points are closed, by having me touch both ends, observe what happens. The green LED lights up. This suggests that I am an inductor and also possibly have a certain capacitance. Now, let me take a step back and explain the differences between a conductor, an inductor, and an insulator. A conductor, simply put, is any material that allows energy to flow. An insulator, on the other hand, is any material that limits the free flow of energy. An inductor is any material that stores energy within its magnetic field. And another concept I should mention is capacitance. Capacitors are where conductive material are separated by insulators, and this creates a unique situation where it can store and discharge energy. This is a traditional test pen without the induction circuit board, and when I close the circuit by touching both sides, nothing happens. This is because this is primarily designed to test for voltage ranging from 100 to 150 volts and was not designed to pick up induction fields.
We will start off our test with 3 modern coins. 2 of them are ferromagnetic and 1 is made of aluminium bronze and does not react to a magnet. Bringing our testing pen in contact with all 3 coins and we get an immediate response. Now we introduce another 4 items made up of various materials, an iron ball which reacts to a magnet, 2 different pieces of wood from different species of trees, and a cabochon cut gem that reacts to a magnet as well. Here we see an immediate response as soon as the test pen makes contact with the iron ball. As expected, there is no response when contact is made with the 2 pieces of wood. What was unexpected was that there was no response when the magnetized cabochon makes contact with the test pen. Here I have another mineral specimen that is known to contain some natural iron inclusions, which is easily magnetized as well. Although somewhat faint, there is clearly a response when the test pen makes contact with this mineral gem. Next, I introduce 3 samples of iron. 2 of them are meteorites. 1 has been cut and polished, while the other is in its raw form. And another example is refined, high-carbon iron ore. High carbon, or in its purest form, is brittle and breaks apart easily, as you can see here. Now here is the kicker. Did you notice that the test pen no longer has any response when contact is made on items placed on the black base tray, unless I am touching the specimen examples? Observe closely. This coin in my hand, the test pen lights up. When placed on the green mat, the test pen also lights up. But the moment it is on the black base tray, I am not able to get a response from the test pen anymore. What do you think is happening here? Let's see if the other items is facing this outcome as well. Keep observing and see if you are able to figure it out. Have you figured it out yet? The answer may come as a surprise to you. This is a classic example where one overlooks a very important environmental factor: static and electromagnetic contamination. The surface of this mat has been charged with an electromagnetic field, possibly from the equipment cabling that is running under the tabletop. We have now moved to another room that is free from static and electromagnetic contamination. We are still using the same test pen. Observe that there is no response, even when contact is made by the test pen onto the table mat. We are also using the same items as before to conclude our test. The findings are interesting. It would appear that on a surface that is insulated and free from static and electromagnetic contamination, objects that are possibly conductive in nature no longer possess an inductive charge that will cause a response when in contact with the test pen. In theory, this could be the foundation science of removing invulnerability and invincibility from one who is not affected by bladed or projectile weapons. If the myth can be proven to begin with, here's an added bonus from my personal collection: a ring with the fabled Bessie To'o as its gemstone. We can now safely conclude that the environment plays an important part in such testing as well. It is not a miracle to marvel at, after all. It is simply science. With the appropriate tools, the proper outcome will be achieved. Just because an object causes an induction tester to light up does not immediately suggest that the item is special.
Hey, if you have learned something new from today's video, do have a care and remember to subscribe, like and share if you would. Your support will help this video reach out to other kris enthusiasts out there and will allow them to discover and explore deeper into the facets of kris collecting in upcoming videos. Do share your thoughts and questions in the comments below, and let's weave the future of Keris collecting together. So here's my conclusion. We must avoid being overzealous and too quick to marvel at what we see. Curiosity is great, but it must be paired with a deeper understanding of the concept and context behind any discovery. Without this, we risk misunderstanding or even perpetuating falsehoods. Equally important is a grasp of basic scientific principles. These are the tools that allow us to think critically, apply logic, and separate fact from fiction. Without them, we are left vulnerable to sensationalism and misdirection. And to my fellow content creators, we have a responsibility. When we share information, ensure we explain the finer details and the context surrounding it. Half-truths might generate buzz, but they mislead and misinform. In the realm of Malay material culture, for instance, I find it deeply troubling that so many outlandish claims are being presented simply to create hype, while the truly fascinating and factual data is often ignored or dismissed as boring. This, in my view, is unacceptable. As a content creator, I feel a duty to step in when necessary to provide context and clarity, even if it means challenging the work of others. Facts matter, and I will continue to advocate the content that respects logic, science, and authenticity, because at the end of the day, this is the responsible thing to do. Well, that concludes today's video. I hope it broadens your minds and may you be able to understand how being a responsible and credible content creator creates meaningful impact to the lives of your audience and yourself. If you missed my previous videos, you can watch them right here. Until my next video, stay curious, start exploring, and keep the legacy of the Keris alive.